Okay, so today we are going to start new data structure title, which is graphs. So this data structure is pretty much essential and very useful data structure when it comes to computer science. So there are so many applications that we can do by using graph and graph theories. So before move to that part, let's take a brief look out about what is this graph mean, right? uh, so I have created few slides to that also, but this is very brief introduction about graphs. So if you need to more uh, information or more details about this stuff, better look out some resources instead of just watching these slides. Okay, these slides are mainly focused for the major aspects or the core contents of the graph theories. It doesn't reflect everything about graph theories. It's just show the main things. Okay. So graph is representation of elements and their relationships. So in a graph, what we have is first we have elements, then we have their relationships. That's what graph means. But when it comes to computer science, we are not calling those elements as elements or relationships. We are calling vertex and edges. So basically, vertex mean the element or a member. Okay. So edge mean basically the a relationship between a couple of edges. Okay. So in here, this is the very formal graphical representation of a graph. uh, Again, it doesn't mean this is the only way to represent a graph. There are so many types of graphs. This is just a very basic representation. Okay, there are very complex graph over there, but in order to get some understanding, first we have to go with simple things. Okay, so this is how we represent a graph. Okay, these round things can be called as vertex, and these lines are edges. Okay, this is just a graphical representation. Okay, we are not representing graphs in a computer like this. Okay, that's why we use data structures. Okay? There are specific data structures we are going to learn later. For now, just remember this is how we represent a graph. Right? These things are known as vertices, and these things are known as edges or arcs. Uh, and I forgot to tell you that what are the applications of graphs. So there are a couple of applications we are using generally when it comes to graphs. So the first thing is to model computer networks. Okay, it is a very versatile uh, procedure when it comes to modeling networks by using graphs. And of course, if you are familiar with social network, most probably you are familiar with social networks actually. Uh, so in social networks also, in order to represent the friends or in order to represent the relationship between users, we are using these graphs. Okay. Uh, okay. So forgot to tell you that what are the applications of graphs. So there are so many applications, but when it comes to general aspects, most probably we are using graphs to represent some networks. So to model computer network is one of the major application that we can do by using graphs, because it's so pretty much versatile uh, to in order when it comes to representing networks or network behaviors. Right. Uh, And if you are familiar with social networks, of course, most probably you are familiar with, uh, in order to represent the relationship between friends or relationship between multiple users, we are using these graphs. Okay, uh, so those are the basic, or let's say those are the very general way of the general applications of the graphs. Okay, but there are so many things. Actually, we will learn those things later, like find path algorithms, A star algorithms, DAGs. Uh, then we have something known as spanning trees, uh, and there are so many things. Okay, so we can discuss those things later. But for now, just remember there are so many applications. Okay, and yeah, so graph types. So there are three types of graphs. First one is undirected graphs, second one is directed graphs, and multi graphs. Okay, again, these are the major deviations of the graphs. Okay, there are so many deviations, so there are so many varieties when it comes to graphs. These three are just basic uh, deviations. Okay, so first thing is undirected graphs. So in an undirected graph there is no direction in between two vertices. That's why it's known as undirected. Okay, therefore all the digits are undirected. uh, so let's take a look at this graphical representation. Okay, so in here we have 1 2 3 4 5 vertices and 5 edges also. Okay, so what is this undirected means? uh, Normally this edge or normally this arc can represent a specific way if we want, but in this special case we are not representing any uh, special direction. Okay, like if you want to represent, let me show you by using a pen. So if you want to represent the way of 1 to 2, then you can represent it like this. Okay, so if you want to represent a way like 4 to 3, then you can represent like this. But the thing is, when it comes to undirected graphs, actually there is no specific way, which means either you can go this way or you can go this way. Okay, normally when it comes to undirected edge, uh, this edge representing both ways, which means 1 to 2 and 2 to 1. Okay, then 3 to 4 and 4 to 3, then 3 to 1 and 1 to 3, 2 to 4 and 4 to 2, then 4 to 5 and 5 to 2. So there are 1 2 3 4 5 6 7 8 9 10 directions uh, which has been defined by this graph. Okay, so that's what undirected graphs mean. There is no specific way to go all over. Okay, uh, okay, so there are two types of undirected graphs. First one is just normal general undirected graphs, and second one is weighted undirected graphs. So these are very important things. First, look out undirected graphs. So as I explained before, undirected means just there is no specific direction. It's just like pointing to the both ways. Okay, it just represents a connection per se. Okay, so weighted undirected means then these edges represent some weight. Okay, let's say a priority or some integer that represent in the weight. Okay, So in here you can see 3, 8, 6, etc, etc. There are so many weights over there. So what does this mean by 3 is, when it comes to 1 to 2 relationship, it has the priority of 3, or it has the weight 3. It represents some let's say some amount, some special uh, amount of prioritization. Okay, normally we are known as it's a weight. So when it comes to weighted undirected graphs, every edge represents some weight. Okay, that's simply like that. Okay, so this is the second type of graphs, which is directed graphs. So this is what I am said before. When it comes to undirected, there is no specific way, but when it comes to directed, there are specific ways. Okay, or there is a specific way in between two vertices. So in a directed graph or digraph, there is a defined direction in between two vertices. Therefore, all the edges are undirected, or all the edges are directed or undirected. So this is very essential actually. What is meant by directed and undirected in a directed graph? The thing is like that. As I said before, if some two vertices are pointed to the both ways, then it means there is no specific direction. It's undirected. So likewise, when it comes to directed graph, what if there are two relationships or two edges in between the same edge, the same couple, the same batch of edges, like in here. So 2 to 4 is one edge, 4 to 2 is another edge, but both edges are pointing to the same two vertices. That means it's undirected. It is the undirected behavior. Okay, so that's why it said in a directed graph there could be undirected edges. There could be. Okay, but when it comes to directed graph, or let me show you, when it comes to directed graph, there is no directed path. Okay, all and every edge is undirected. But when it comes to directed graphs, there could be having directed or there could be having undirected, both parties. So those are very simple things. And as I said before, in the undirected graphs, of course, in the directed graphs can be derived as two parties, two things, or two types. As the first one is general directed graphs, and the second type is weighted directed graphs. So directed graphs is normally like that, and directed graphs contain some weight or some priority in between their relationships or in between their edges. Okay, so the question: how to represent a graph in a computer or in a virtual manner? Okay, so this is where programming occurs. Okay, so there are two major ways to represent graphs. So that is why I said before, when it comes to computer science, we are not representing graphs in a graphical notations. Okay, so because it even it is very familiar to the humans, I mean us, it does not reflect. That is the most efficient way to represent graphs. Okay, uh, when we are dealing with data and when we are dealing with programming, we can't represent graphs as graphical notations. Okay, we should use some specific data structures to represent graphs. So that's why we are using these two major data types. First one is adjacency matrix, which is normally a 2D array or maybe a 2D vector. Then adjacency list. So adjacency list is basically a linked list or maybe a pointer linked list, or maybe we could use a vector as well. Okay, so just remember, adjacency matrix is basically a 2D array for now. Okay, and adjacency list is basically a pointer linked list. Okay, so just remember, I'll explain these things later. So let's look cover adjacency matrices, the first type. Okay, so undirected graphs, adjacency matrix. So we can represent a graph as a G equals V E in a mathematical way. If you're familiar with uh, what we call this, if you are familiar with the geometrical features in mathematics, we are represent a specific location by using two how do I say this, 2 points or some two variables. Okay, like when it comes to graphs, we are representing vertices and edges uh, like this. Okay, so this is just a mathematical way. So V means the set of vertices, E means set of edges. So imagine V as a set contains all the vertices that contain a graph, that contains in the graph. So like this, according to this graphical representation, this contains two vertices. First one is 1, 2 and 3. So it can be represented in a set V 1, 2, 3. So how do we represent edge? So edges also can be represented as a set, but it should be contain all of these vertices as well. Okay, so that's why we using these type of sequence. Okay, so 1 2 means so let me use my pen. So 1 2 means this relation. Okay, so 2 1 means this relation. Okay, so I'm not going to say relation again, I'm using edge. Okay, because when it comes to data structures, we are not using relationships. We know it as edge. Okay, so 2 to 1 is another edge. So 1 to 3, 1 to 3 is another edge, 3 to 1 is another edge. Okay, and 2 to 3 is another edge, 3 to 2 is another edge. Okay, so we have been successfully represented all the edges that contains in this graph by using a set. Okay, so that's why I said before, when you are specifying an edge, someone could ask why we can't represent the edge by using just 1 and 2. Why we are representing is 1 and 2 and 2 and 1. This is the thing. When it comes to directed graphs, when it comes to undirected graphs, it is not necessary to represent actually by these two types. But when it comes to directed, we have to represent direction also. So that's why we are using these type of method. So basically, suppose an arbitrary edge like 1 and 3 from set E. So this 1 means the out degree and 3 means the in degree, which means 1 means that is the place where let's say the arrow started, and then 3 is the place where arrow points to. Okay, so basically 1 3 means 1 2 3. Right, so those are very simple things, you can get the idea very easily. Okay, so this is the pretty much important things in today's video, I think. So since all the vertices in a set we can represent it, yeah, it's just using a square matrix. So if you are familiar with mathematics or pure mathematics, you know pretty much well what is this matrix means. Matrix means the representation, abbreviated representation of data or data collection. When it comes to square matrix, we know that matrix is having same number of rows and same number of columns. Okay, that's why it's known as square matrix. So imagine a square matrix like A. So it contains now 1 2 3 and 1 2 3 3 columns and 3 rows, which means it's a 3 by 3 square matrix. Okay, so if you are dealing with 3 vertices, then you have to use these 3 by 3 square matrix. If you are dealing with 5 vertices, then you have to use 5 by 5 square matrix. If you are dealing with millions of matrices, now that's a kind of a problem, this data structure also. I'll show these stuff later. If you're using 1 millions of data, 1 millions of vertices, then you have to use uh, 1 million by 1 million square matrix, which is pretty much not a good way to represent a data set. Okay, because it's takes a lot of memory in the execution as well as storing. But for now, just remember we can represent a graph by using adjacency matrix like this, by using a square matrix. Okay, so this is 1 2 3 and 1 2 3 means the vertices, and why I coloring this as red, because these are the out degrees, and why I'm colored these three things as the yellowish color, because these are the out degrees. So when you're pointing some edge 2 to 1, then this we can represent it by a 1, because there exists some edge. If you are pointing some edge to 3 to 1, then it can represent it as 1 again. Imagine there is a no edge between 1 to 1, then it is basically a 0, because there exists no edge. So if you go through all over these data sets, you will realize what a graph I represented, or what graph I represented in here. So it is just basically this graph. Okay. So 1 to 2, 2 to 1 relationships exist. So 1, so let me use my pen. Okay. So 1 to 2 exist, 2 to 1 exist, then 1 to 3, 3 to 1 should be exist, then 1 to 3 exist, and 3 to 1 exist, and 2 to 3 and 3 to 2 should also be existed, and those exist as well. And these diagonal values are remain 0, because we have no relationships like this: 2 to 1 pointers, 3 to 3 pointers, 1 to 1 pointers. We have no relationships or no edges like that. Therefore we can't represent our diagonal values as 1. Diagonal values mean these types of values. Okay, and the another major thing that you can see when it comes to directed graphs, if you are representing directed graph by using matrix, then it is for sure symmetric. Okay, it should be in symmetric manner. If it is not in a symmetric manner, then you have done some mistake. Either you are not representing a directed graph, sorry, undirected graph. Okay, uh, so this title is wrong. This should be undirected. Okay, so that's my mistake. Okay, so implement an undirected graph using adjacency matrix. So let's look at that one also. So this is where programming occurs. Okay, so let me create a new document for that. It's not a new document, it's a new file. Okay. So, and let's say I'm just using test. Okay. Test CPP. So I'm using DevC double plus for my scripting purposes, but you can use any kind of scripting software like Visual C++ or anything suitable to code C++ programs. Okay, so first we have to specify our specific library, IO stream. Then we have to specify our namespace. You know these stuff when it comes to C++, we have to represent namespaces as well. So this is our main function, and we need a matrix known as, it's a adjacency matrix, which having a maximum amount of rows as 100%. So max, and again max. Oh, wait a minute, my tea is spoiled all over. Okay, back again. So sorry about that. So this is our 2D matrix. Then we need a function to initialize this matrix as 0 in the beginning. Initialize mat. So in order to do that, we need how much amount of vertices we are going to use. Therefore, I'll specify another variable here also, vertices. So let's say 3 in this case. And when it comes to initializing, okay, initialize, sorry. So initialize matrix. So we need 2 for loops like this. Then first loop having something like this, 1 to v plus plus. Then same thing but different variable. So j v j plus plus. So now okay, we have to pass our adjacency matrix as well as a parameter. So instead of just passing, I will use this as a global variable, so it will be easier for you maybe, but of course you can pass it as a parameter as well. But this is just a simple example, therefore I will use this our adjacency matrix as a global variable. So I'll take my adjacency matrix like this and initialize my ij place as 0. So initially my matrix now contains zeros according to how much vertices I'm going to use. Then I can define another function to add edge. So this probably contain 2 parameters. So first one is adjacency matrix u v must be 1, as well as adjacency matrix b u must be 1. So now I can add edges. So if I go to my presentation, where did I stop? Over here, right? So if I use if I use this graph, then that it just will be 1 to 2 and add edge 1 to 3 and add edge 2 to 3. So those are the edges. So since we have been successfully defined our edges, we can display our adjacency matrix. So I'll just simply name like this, and int v means number of vertices. So probably you know that when it comes to displaying 2D array or 2D matrix, we need for loops. But in here I starting from 1, okay, because we are using 1 2 3 vertices. We are not using 0 vertex over here. That's why I used 1 over here. V I plus plus. Likewise int j 1 v j plus plus. So what's that? Okay, and it should be equals to the v, otherwise it will go only for 1 and 2. It will not point to the 3. Okay, so how can I display this? So in here I can use like this. See out. So first over here maybe see out another for loop representing our elements. Maybe could I be less than me I plus plus. So see out like this I. Okay, I think this will be fine. Then end line, of course. Then see out I, and again tab space, then see out. So now we are displaying our matrix values. So I minus 1, j minus 1, and tab space as well. After all, a new line or end of the line. So now I think we can display by using our 3 vertices, and after all we are returning our default 0 value. So let's compile, hope there is no errors. Okay, so there is no errors. Let's execute. See, now it represent our graph, but there are some problems. So 1 2 3 should be there, which means there should be equal sign. And why it doesn't reflect our 1 and 3? So let me quickly check. Sorry. So 1 and 2 is not over there. Why is that? 1 and 2. So initializing complete successfully. 1 and 2. 1 2 equals 1, 2 1 equals 1. Okay. This is the mistake over here. I used like this. This is the complete bullshit. We don't need to specify like that, because since we are using just directly our matrix like this 1 to 2, then it should be printed 1 to 2. Okay, we don't need to decrement our values. So here now we have been successfully represented. Where is it? This adjacency matrix. See, 1 2 1 is there, 1 2 is there, 3 1 is there, and 1 3 is there, 3 2 is there, and 2 3 is there. So this is what I wanted to show today, how we represented undirected graph using adjacency matrix. Okay, so I hope today's lesson is too clear for you, and we will meet another lesson in later. So thank you.